Hello, I'm Nikhil Varma Keetha, a robotics and summer scholar at the Air Lab, mentored by Dr. Chen Wang and Professor Sebastian Skedder. I will be presenting our work across the summer, AirObject, an evolving topological graph-based object encoding for semantic loop closure. This work was done in collaboration with Dr. Chen, Yuang, and Professor Sebastian. Well then, you might be wondering, why is object encoding and matching important? Object matching is crucial for multi-agent robotic tasks such as autonomous exploration, semantic mapping, with potential downstream applications in search and rescue, augmented reality, and many more. This task of object matching is especially hard because it requires object encodings which are robust to viewpoint shift, occlusion, and deformation. Furthermore, distinct features across multiple viewing angles make the task even harder. Another challenging aspect is the requirement for these object representations to be shared and merged across multiple agents effectively. Intuitively, an object can be represented as a graph, where each node of the graph represents a distinctive feature, while graph structure provides info regarding object structure. However, these graph structures vary with time due to various reasons such as occlusion, deformation, as seen on the left, and viewpoint shift, as seen on the right. Hence, there is a requirement for building an evolving graph representation of an object to accumulate knowledge across multiple viewpoints and provide robust semantic matching. So, how do we exactly build these evolving representations? We firstly start by inputting an object video sequence to a GNN based object encoder. So, what is a GNN? A GNN is a deep learning architecture which leverages structural context from graphs. To enable this, it uses a technique called neural message passing. Neural message passing can be imagined as neighbors of a particular node sending messages. This simple yet effective concept helps a GNN reason about structure of the data. With this in mind, we design an object encoder containing a node encoder which encodes superpoint keypoints, which are later on passed to a two-layered graph attention network, which is essentially an attention-based GNN. Furthermore, we have a encoder and location encoder which predict element-wise content and location features respectively. These features are element-wise multiplied and input to a single layer encoder to get object descriptors. We leverage the location features to perform topological graph merging across various frames to build an evolving graph. We then reconstruct a superpoint based evolving graph which is input to the object encoder to get the 3D object descriptor. This 3D object descriptor can be compared with other 3D object descriptors or single frame descriptors for robust matching. To test the efficacy of our proposed method, we use a dataset called YouTube video instant segmentation, which has a large object vocabulary and various challenging scenarios, including multiple animals and people riding on vehicles. For testing, we build 3D object descriptors from the first half of a video sequence and match with the 3D descriptors of the second half. To compare the performance of our approach, we use two baselines, namely 2D and 3D, where the 2D baseline matches single frame descriptors while the 3D baseline matches object descriptors obtained by averaging the single frame descriptors. From the table and precision recall curve, it can be seen that our proposed method shows substantial improvements over the baselines. Furthermore, we show a GIF representing new points added to the evolving graph as we traverse the video sequence. It can be seen that a large number of new points are added when the viewpoint shift is large and new distinct parts of the object are visible. This shows the robustness of our proposed graph merging process. With this, I would like to conclude with a thank you note. I thank Dr. Chen, Yuhang, and Professor Sebastian for mentoring me across the summer. Furthermore, I would like to thank Rachel Bursin, Dr. John Dolan, Jenny, and my fellow RISC cohort members for this wonderful summer experience. Thank you.